In addition to the relationship of linear independence and redundancy when you take span, there's another reason to be interested in linear independence of vectors. And it has to do with trying to use vectors as a coordinate system. So to get us started, let's suppose we have some vectors that are linearly independent, and we have another vector v that's in the span of those. So the question I want to ask is, how many ways can we write v as a linear combination of all the vi's, right? The idea here is, so suppose we're in a plane in some vector space Rn, right? If we have two vectors in this plane, we can kind of use these vectors like a coordinate system. If we have any other vector, then we can, in this plane, we can write this vector as a linear combination of the first two, right? So a multiple of the first one and a multiple of the second one, and add them together, and you get this vector, right? So the coefficients, so this would give us, so let me not call these v's, let me call them w. So if this is w1, this is w2, and this one is w, right? Being able to write w as a linear combination of w1 and w2, it's essentially, right, these scalars here essentially act like coordinates in this vector space, or in this subspace. But I mean, one important thing about coordinates is that, or one thing that you would like to be true about a coordinate system is that there's only one way to write down the coordinates of something with your coordinate system. We know in some cases that's not true, right? In polar coordinates that breaks down for various reasons, but it's something to aspire to anyway. So, so that's why we're asking this question, right? We'd like to use spanning sets as coordinate systems, but first we need to know about how many ways we can write vectors. All right, so let's suppose we have a vector in this span. How many ways can we write this vector as a linear combination of v1 through vk? Well, let's take 2 ways. So suppose that v is a1 v1 plus dot 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 ak vk. And suppose that we can actually write v as a linear combination of v1 through vk in a different way. So say b1 v1 plus dot 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 plus bk vk. All right. Well, if these two things are equal, right, if they're both v, that means they're both equal to each other. So that means a1 v1 plus dot 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 plus ak vk equals b1 v1 plus dot 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 plus bk vk. All right. But now that we have this equation, well, look, there are lots of terms with that have the same vector in them. So let's move everything to the right. We get the 0 vector is minus a1 v1 minus so on up to minus ak vk plus b1 v1 plus dot 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 down to bk vk. And now we can start combining terms. So the 0 vector is b1 minus a1 times v1 plus dot 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 down to bk minus ak all times vk. All right. Well, wait a second. Look at this. Here we have a linear dependence relationship among the v's, but we assumed that the v's are linearly independent. So this means that this has to be the trivial linear dependence relationship. So that means b1 minus a1 has to be equal to 0, and b2 minus a2 has to be equal to 0, and so on, all the way down to bk minus ak has to be equal to 0. Right? And all of this is because of linear independence. Right? All right. Well, if b1 is equal to a1, that means B1, sorry, if B1 minus A1 is 0, that means B1 is equal to A1. And so on, all the way down to BK has to be equal to AK. So, if we go back to where we came from, right, we said we had these two ways of writing V as a linear combination of V1 through VK. That means these two ways, well, AK is A1 is equal to B1, and so on, all the way down to AK equal to BK. That means that these two ways are actually the same. So what we've shown is that if you have linearly independent vectors for each V in the span of all of those vectors, V, we can write V as a linear combination of the VI's in a unique way. And that's the key thing, right? In a unique way. So that really is one of the most important things about linearly independent sets, right? They give you a unique way to express anything in their span. That means that this sort of geometric idea we had, that if you have two vectors in a plane, any other vector is uniquely expressed as a linear combination, so these coefficients can be used like coordinates. This generalizes to larger vector spaces, or even vector spaces that aren't inside of Rn. So this is a key aspect of linear independence. And in fact, even better than that, this is a big example, or a typical example, of how linear independence gets used to prove things about vectors, right? You somehow come up with some equation, depending on, what sort of situation you're in, and you somehow turn that equation into a linear dependence relationship. And then, if you know the vectors are linearly independent, that means every coefficient in this dependence relationship has to be 0. And then you can often extract information from all of these things being equal to 0, right? In this case, extracting that information was just moving the a's to the other side. So this is a really typical way of using linear independence in proofs.